Good afternoon, sir.
Good afternoon. Good afternoon. So today is our last session, and we have gone through all the questions we were supposed to solve. And last session we finished the chapter 12, and I'm here to solve your question today. If you have any requested a specific problem, just let me know. I can solve it for you.
I didn't. I'm doing now. I did yesterday, and
Okay.
the day before I did chapter 5,
Okay.
and now I'm doing Lagrange. So yeah, I don't have any questions for like the later chapters, but yeah, I just started pretty much like Lagrange. I tried to understand it, and now I'm trying to practice. But when there's like swinging bars, I find it a bit complicated, you know, to write the Lagrange equations. But
Okay. The double pendulum, you mean double pendulum, or
either double pendulum or double, like I don't know if you have the book. I'm gonna tell you which question it is.
Yeah, I have. Okay, I saw your point. This
it's a like problem 7.17. Yeah, like this. Right? Yeah.
So
with the spring.
7.17.
Yeah, I think there is a spring in the middle.
Very important, right? Because I solved one of the final problem in the Lagrange session. There was a.
Oh yeah, with the yeah.
Okay, I'll try to go to. This is very important. Lagrange is very important. So you did mention very good questions. I solved the double point. It's more or less the same, but for Lagrange, all you have. The important thing is just okay. All you have to do is just finding the calculating the total kinetic energy and then total potential energy. So as I told you, for the first bar, it's very simple, which is attached to the point O. But calculating the kinetic energy of the second bar is a little bit tricky, because the first bar is only the total kinetic energy of the first bar can be easily represented and written as a pure rotation around point O, or you could write it easily as a rotation around center of gravity. There is a pure rotation around center of gravity, and there is a basically linear motion. So for the first mass, there are two approaches for the first mass. As I told you, it is better to go for total energy, total potential energy around point O, or a linear kinetic energy around point G plus rotational motion around point G. So both approach will give you the same answer as I solved in the previous problem. So for the first mass, it's very simple. All you have to do is just the total kinetic energy of the first bar is 1/2 J naught theta double dot 1 square. What is theta what? Theta 1 is just theta 1 is this angle and theta 2 is this angle, right? Two independent generalized coordinates in order to represent the behavior of the system at any time. So theta 1 and theta 2, the first step is to apply Lagrange, is just determining the number of degree of freedom system. So as soon as you look at the system, you will notice that we need only two generalized coordinates, theta 1 and theta 2, to represent the motion of the system at any time by only theta 1 and theta 2. So theta 1, for the Lagrange, the main important step is calculating the total kinetic energy. So you have to independently calculate the total kinetic energy. For the first bar, it's very simple. All the kinetic energy, we could take a look at the first bar, and it can be understood that the first bar as if it is only merely rotating around point O. So this can give you simply the total kinetic energy. So 1/2 J, according to the parallel axis theorem, J around point O for the first mass, for the first bar, is J around point center of gravity of first mass, first bar, plus md squared, md squared. D is a distance between the two center of gravity and point of rotation. So m is given. So you can easily apply it, and I think is somehow, I'm not sure, 1/12 m L square. L is the length of the first bar, plus m half L squared. Theta 1, theta dot 1 squared. So if you have if you're okay with calculation the first bar, the kinetic energy of the first bar, just let me know. Is it easy or is it hard? Just let me know for the first.
I think it's okay because you see, forgot. I thought I was. We should do it by just the center of gravity, but doing it with the around O, this gives like the parallel theorem, something like that.
Exactly. You could go for the center of gravity, more or less the same, because you know, if I further simplify it, 1/12 ml squared plus ml squared over 4, right? Yeah. So I multiply the denominator by 3 and the numerator by 3, yeah, right? So theta dot 1 squared, therefore this is going to be 1/2 12 1 plus 4, 1 plus 3 ml squared theta dot 1 squared, and is going to be 1/2 multiply 4/12 theta dot 1 squared. I forgot to put ml squared here. So this is going to be 1/6. Is it true or not? Okay. Totally is correct. Totally is m. Totally is okay. 1/3 ml squared theta dot 1. This is the total kinetic energy of the first mass. The second approach you mentioned, you could go for that approach. Both approach is the same for calculating the first mass, okay?
Yeah, it's going to be the same thing because center of gravity, I think it's ml squared over 3.
Exactly. So for the first mass, so our focus will be go for center of gravity. So at the center of gravity, there is a velocity like this, angular velocity Vg is half L theta dot 1 squared. This is the velocity, right? And so there is a rotation. So the kinetic energy for the first bar would be 1/2 m Vg squared. Center of gravity has linear motion plus rotational motion, 1/2 jg 1 theta 1 squared. So 1/2 m Vg is half L theta dot 1 squared plus Gj is 1/12 mL squared. By the way, it is for the second mass, you don't have any other options. For the second mass, the approach is the same, like this, linear motion, rotational motion. You could go it for the first mass if it's depend on you. So Jg theta dot 1 squared. So I was trying to mention you could stick to this approach. Is it okay for you? No problem. So half L, half M, L over 2 squared. Okay, I made a mistake here. Sorry, I should have written like this. A little bit messy here. Okay. Vg squared is here. Be careful. S squared is out of parentheses. Vg is half L theta dot 1. Vg squared. So 1/2 m Vg squared L squared 4 theta dot 1 squared plus half L half 12 ml squared theta dot 1. So all you have to do is just take a factor out from the two. So factor out the similar part. So you have to make summation between the two. So here I can write 1/4 ml squared plus 1/12 ml squared, which is the same. So here you put a denominator 3 and numerator 3. Therefore, it's going to be the same results. 1/2 1/3 ml squared theta dot 1 squared. So either you are facing with double pendulum, double bar, you could stick to this approach. Just put your focus on the center of gravity of each bar in order to calculate the kinetic energy for the first, for the second.
And for each of the bars, there is a velocity which is like in a straight line and a rotational velocity which is represented by JG.
Exactly. For the first mass, everything is very simple. However, for the second bar, is little bit tricky because
it's going to be a relative velocity as well.
Exactly, because the one end, two ends basically are rotating and are moving. So
in different speeds.
Exactly. So this is, so we are done with the first. bar for the second bar. So just put it like theta 1, and for the second bar, again, you have to put all your focus to the center of gravity. So center of gravity for the second bar. Of course, there is a rotation, and there is a basically velocity applied here, VG2. However, VG, for the first mass, if you remember, VG1 was respect to the point O. Point O is 0. So VG1 with respect to the point. So here for VG2 with respect to this point, let's say point A, or point 1. Let's say point 1. So VG2 basically, VG2 is VG1 plus VG2 with respect to VG1. So this velocity is applied to this point. So all the particle in the second bar is subject to this velocity. So therefore, I just transfer the velocity here, VG1. You have to make a summation between the two vectors. I gave you the formula.
Yeah.
So I should have written like this. This one basically is VG2 with respect to VG1. This one. This is okay. VG2 with respect to VG1, and this is basically VG1. So VG2 is this, is the summation of the two, VG2. So you have to write this in the exam. You have to write the vector formulation, and you could draw this shape, this figure, and then you can apply the formula. So you have to write like this: VG squared is VG1 squared plus VG2 with respect to VG1 squared plus 2 VG1 multiplied by VG2 with respect to VG1 cosine theta 2 minus theta 1. The angle between the two. The angle between the two, which is not very important because both of them we are assuming a very, very small motion. Theta 1 minus theta 2 is more or less 0, cosine 0 is 1. But to show you why is so. Theta 1, theta 2. So here, this is 100 degree, right? So basically, these two is just, it's very, very, I cannot focus on this.
It's okay. I think it's is it 180 minus minus theta 2 plus theta 1. Something
This
like
this angle is, I was trying to mention that this angle is theta 2 minus theta 1.
Okay.
And so here is theta 1, theta 2. Okay. Okay. Theta 1 is this angle also. Okay, I see. Here, this angle is theta 1, right? This is going to be theta 2 minus theta 1, right? This angle. So since so this angle should be the same as this y, because this side is perpendicular to this side, right? 90 degree here, and this one also perpendicular to this one. This one perpendicular to this one. That's why you could say these two are the same. So this is alpha, this is alpha. This should be the same. Why? Because this is 90 degree and this is 90 degrees. I mean, this side is perpendicular to this side, and this side of this is perpendicular to this. Therefore, you could draw a conclusion that these two are the same. So the formula for the chapter Lagrange 7 point. Yes, cosine theta, exactly. So the formula is correct. So here it's just almost 0. Cosine 0 is 1. Vg squared. Vg1 is half L theta dot 1 squared. Half L theta 1 Vg1 squared, Vg1 squared plus Vg2 with respect to the relative velocity, which we obtain as half L theta dot 2 squared. Half L here. The second, this Vg with respect to the Vg1. It means that when you are reading Vg2 with respect to Vg1, it can be translated like this. Vg2 with respect to Vg1, it means Vg1 is constant, is O, is stationary. Then you calculate VG2 with respect to VG1. It means VG1 is constant, is stationary. So plus 2 VG1 half L theta dot 1 VG2 half L theta dot 2. So then you can calculate the basically VG, the total velocity for the linear motion of the second bar is L squared 4 theta dot 1 squared plus L squared 4 theta dot squared 2 plus L squared theta dot 1 theta dot 2 over 2, right? So this is the only, as soon as you opt, it's very important. It's very, very important. Once you obtain VG2, all you have to do, the kinetic energy associated with the second bar is 1/2 m2 VG2 squared plus 1/2 J2 around point center of gravity theta dot 2 squared. So this is the linear motion of center of gravity, and this is rotational movement. So kinetic energy associated with the rotational movement and linear movement. So VG2 is obtained. GJ2 is again 112 m2L squared. That's it. So let me check the final answer. 7.17. I think we solved it in the class, right? 7.70. I solved in the class. So
yeah, I think you did, but it's okay for the answer. I got
okay.
it. Yeah.
So,
it was just to understand the principle of the velocity, since it's been a long time since I didn't do this.
I see the point. It's very important.
Adding vectors and using cosine law to find this.
Just go for this this approach. This approach, the vector formulation.
It's pretty easy. It's just in the exam, it's a lot to do. You know, I think there's a lot of small tiny things where errors can be made, like just adding L over 2 and it's squared and it's
yeah,
and then
exactly.
there's 2. Yeah, so there's a lot of small mistakes that can be done.
I see your point. Yeah. Yes, like me, I did now. I will show you. This is my mistake. I made a mistake here. I will show you why. So VG1, that's very good question. I made a mistake, very tiny mistake. You were talking about that. I did here. So VG1 is half total watt squared. Okay. VG2. Okay, VG2 is, that's it. I made a mistake here. You know, it is wrong. I made a mistake. VG1. It is better to write. Okay, I made a mistake here. Here I made a mistake. VG1 is not. This is wrong. This is wrong. So let me show you. It is better to use this notification. Okay. So there is a first bar. There's a second bar. Okay. let's call this point O. Let's call this point G1. Let's call this point G2, and then let's call this point A, okay? The second bar is rotating around point A. So for the first bar, the kinetic energy was simply 1/2 mvg1 squared plus 1/2 gj1 theta dot 1 squared. That's it. So where is VG1? VG1. Basically, this is the VG1 and theta 1, and this length is 1/2 L. Okay, VG1 is 1/2 L theta dot 1. So we are done with the first bar. The kinetic energy of the first bar is done. Simply. Very simple. The first term associated with kinetic energy 1/2 mvg1 squared plus the second term rotational movement 1/2 gj1 theta dot 1 squared. And VG1 is 1/2 L theta dot 1. However, for the second bar, there is this velocity is VG2 with respect to A, VG2 with respect to A, and at point A, there is a velocity associated to the rotation of the first bar, VA. Therefore, if I separate the second bar, VA can be transferred at any point. All point of the second bar is subjected to the VA because it's attached to the point A to the first bar. Therefore, at G2, there is a basically VG2 with respect to VA and there is a VA. Therefore, I should have written like this. If I magnify it, VG2 with respect to A, it means if point A was a stationary, G2, the rotation of G2 with respect to the point A, there is a linear velocity VG2 with respect to A. And VA, the resultant vector would be like this. VG2. So you have to write like this. VG2 is VG2 with respect to A plus VA. And VG2 with respect to A is 1/2 L theta dot 2. VA is L theta dot 1. This is VA. VA.
So the previous thing, it was a mistake. It wasn't L over 2, it was L.
Yeah. L over 2 theta dot 1 is just
VG1 for
VG1
the first kinetic energy.
Yes, we have to forget about G1. We have to forget everything about VG1. For second board, we have to only focus on the VG2 with respect to A and VA at this point. This point is very important. So VA here, VA is L theta dot 1, right? Okay.
So we don't have to do the cosine law and everything.
Cosine line is we have to do that. The cosine line is like this. Always we have a cosine line for this pendulum, a second double pendulum, double bar. So this is a vector. We are interested in the value magnitude. So magnitude of VG2 is magnitude of VG2 with respect to point A squared plus magnitude of velocity at point A squared plus 2VG2 respect to A multiply VGA cosine theta 2 minus theta 1. The only mistake we were applied is just
That was VA.
yes. This is the same. So therefore, VG2 is VG half L theta dot 2 S squared plus VA is L theta dot 1 S squared plus 2 half L theta dot 2 multiply VA is L theta dot 1 cosine 0 is 1. So you have to basically use this. So as soon as you obtain VG2, then you could apply and write the second kinetic energy, 1/2 mVG2 squared plus 1/2 mass moment of inertia around point G2 theta dot S squared. And then you make a summation. As soon as you obtain T2, you have to write the total kinetic energy T1 plus T2 and write and put it aside and then go for potential energy.
Yeah, okay. And then differentiate about theta 1, do the whole thing, and then differentiate again about theta 2, right?
Exactly.
Since there is 2 degree freedom.
Exactly. You have to, as soon as you obtain T and obtain U for both of them, U1 plus U2, as soon as you obtain U1 and U2, you have to use the Lagrange equation. So.
And
yes.
Oh, yeah. No, go ahead.
Okay, for each coordinate, as you mentioned, for each coordinate separately, you have to write time derivative with respect to partial derivative of kinetic energy with respect to theta dot minus partial derivative of T over theta plus, that's it. And as soon as you calculate this, and then you will go for second coordinate. So go ahead, please.
Yeah, no, it was just for the potential energy. The first one is pretty easy. It's just at G you do like the cosine thing and you remove the part that like the difference, right? You do the
Right.
difference of height. But for the second one, you need to add the difference in height of the first bar and the difference in height for the second bar, right?
For the potential energy, it's very easy. Always
For yeah, I mean just for the second bar. The first one is pretty easy. The second one, I think you just have to add the two difference.
Yes. Always consider this zero here as a zero potential, and then you have to basically okay, down is positive. Okay, I'll let you. Okay. Okay, always this is zero and upper is positive. If we come down is negative. So this just apply this rule for all the questions. So here we have first bar.
You see this, the teacher didn't explain it like this, but yeah, it's pretty right. If the bars are going up, then it's going to be positive potential energy, and if they're pushing down, it's going to be negative, right?
So we don't care. We don't. It should always work for all the time. We don't know.
Okay.
It's just you apply. You put the system to the right. So if you go for both scenario, you will reach to the same answer for the final equation of motion, because once you take derivative like this,
yeah, it's gonna cancel out the negative.
so once you take derivative of the two is the same.
Yeah.
Because it is a constant number. Irrespective of where you consider, irrespective of zero reference potential energy, your final equation of motion would be the same.
Yeah.
For the second.
Oh yeah, you don't have to do it for the potential energy.
Okay.
I'm okay for that.
Okay. So if I call this second reference, if I call this first reference, for the first one, the potential energy is like this: mg half L 1 minus cosine theta 1 plus mg L 1 minus cosine theta 1 plus half L 1 minus cosine 2. However, this is a total potential energy related to only potential. You can add if there's any spring.
Yeah.
Okay, but here, if I go for the second reference, this is the response. So G2 minus G1. This is going to, okay, minus, okay, minus, minus mg half L cosine theta 1 and minus mg L cosine theta 1 plus half L cosine theta 2. So if you take derivative with respect to theta 1, these are the same. These are the same. You will obtain the same results.
Yeah, perfect. Because the one is gonna be canceled out when we're gonna derive, right?
There is no cancellation because, you know.
I mean, when we're gonna derive, if we for the first equation, we're gonna derive for in respect to theta one. The one like it's 1 minus cosine theta 1. The one is not useful in this case.
Both of them is correct. Both the equations are correct. This is associated with this reference, and this one associated with the second reference. So it depends on you.
Okay.
Lagrange will get you the correct final answer irrespective of where you consider because when you take derivative here, if I individually each term, if I expand this term is mg L2 minus mg L over 2 cosine theta. If you take derivative, this is there is not that one here. This is automatically becomes zero.
Exactly. It's gonna exactly. Yeah.
More or less the same. They are the same.
Yeah. And perfect. Thank you very much for this question.
You're welcome.
Yeah. Since I didn't do the rest of the, I'm pretty okay with the influence matrix. You explained it really well when I did it with you.
Right.
That I'm very okay. It's just I'm scared about chapter 12 and chapter 12. All Holzer, Dunkerley is okay. I think it's not very complicated.
Right.
But it's just the rest. I didn't do it yet, so I don't have any questions for you.
Yes, for the Holzer last session, I just wrote lots of calculation. But you have to only have a vision, have a focus on the last, because for each rotational system you will reach the same calculation, the same formula. For the T1, T2, you could memorize the final, at least the configuration of this formula, and then if you memorize one of them, you can expand for the other. But the approach is the same. Just apply the kinetic energy and apply the second Newton of law for linear motion, and Euler formula for rotation of movement, and then start from the first mass and go for the last mass, and the summation of the torque should be the same, T1 plus T2, and you have to put theta 1 is 1, calculate T1, and then from T2 you have to calculate theta 2, and from theta 2 you have to calculate T2 and then T3, and at the end you could go for yes, go ahead.
Oh yeah, I'm gonna watch your last video since I didn't watch it yet. I'm gonna watch it and do some exercise, and then can I ask you, is it possible to meet to have another small session if I have any questions on like this weekend?
I'm very because I'm going to defend my PhD thesis and this.
Okay, no problem.
And no problem. Just send me an email. I try to respond you.
Okay. I'm gonna ask you questions by email if there is anything. But
sure.
But I'm pretty sure that I'm gonna be okay. I just need to do exercises. That's the only thing.
Okay. Do you see my notepad?
No. Now I see only your name.
What happened? Okay.
Okay.
I have to turn it on. Okay, now.
Oh yeah.
So for the chapter 12, you Holzer method. You said similar to rotational movement for a linear system like this: M1, M2, M3, K1, K2, like this. In the previous session, I did for rotation. The approach is more or less the same. If you write the equation of motion and for each mass and relate x1 theta 1, x2 theta 2, f1 f2. So if you do that, you will reach to this table again. So the table is the same. There is x1, you have to put 1. This is the same for all case. And then you will find f1 like this, the same, basically the same formulation, m omega squared, basically x1. In the rotational system, it was t1 j omega squared theta 1. That's more or less the same, right? So, and then you will go for x2. You calculate x2 like this, x1 minus f1 over k1. So you have x1, then you obtain the f1, and you put f1 here. You put f1, you have x1, you have k1, then you obtain x2. As soon as you obtain x2, you will go for f2. f2 is f1 plus, so this is question 12.27. f1 plus m omega squared x2. Again, so you have to start from the left to the right. I can't give you the number. So number 1 here, x1. Number 2 is calculation f1. Number 3, calculation x2. Number 4, calculation f2. As soon as you obtain x2, just put it here. You have f1, then you apply. You can find f2. Then
yeah. Then same thing for the rest. For x3, it's going to be x2 minus. Yeah.
Exactly. This is very simple. It's not very complicated compared to the other. It's very, very simple. So
and when do we stop? Sorry, I didn't hear you. I said when do we stop? When we get f equal to 0?
Very good question. Very good question. You know, as soon as you to f2, you will go for x3 and then f3, and as soon as you obtain x4, and the last step is very important. The last step for the last force, this should be 0. If it is, for example, 200 or minus 300, you have to change the first. So you have to make a guess at first step. You have to guess omega 1, for example, 10 hertz, and x1 is always 1. Just give a random number for the natural frequency. If the last force or last torque is 0, your guessed one is correct. However, if you obtain 200 or it's very other number than 0, you have to change your first guess. For example, you can put 15 or 25. You have to change the initial guess. So because only the system only vibrate, because free vibration, when there is no damping, as soon as you apply initial condition, it will be vibrate without any external force. So only if we take a look at this phenomenon in a reverse way, only the natural frequency that can satisfy this equation, summation of force or summation of torque, should be 0. Because there is no any, for a system with any damping, and only natural frequency can satisfy this equation. Because in the chapter 2, we learned that as soon as we perturb and displace the system with initial condition, the system will be vibrate forever, and the frequency of vibration is a natural frequency when there is only damping. So here is like this. We want to find the natural frequencies. So only natural frequencies correspond to the case that there is no external force. As soon as your initial guess reach to the point that the last external force is 0, therefore your guess one is correct. But you have to be very careful. If you put omega and then it is increasing, you have to
if
omega. If
okay,
they become negative and positive, the omega should be between the two. So omega 1 comes up to 200, omega 2 resulted in minus 300. So the correct is between omega 1 and omega 2, right? You have to just...
So if omega 2 increased, then I have to choose something less than omega 1.
Yes, if the force increase, right? If the force increase, exactly. You have to choose other number, exactly.
A number less than the person. Okay.
Exactly.
I guess he's gonna give us the first guess.
I think so, right? I think so.
Yeah.
But you have to formulate correctly F1, F2, F3, F4, and also theta 3 and theta 4. This formulation is very, you have to derive that. If it is given to you, it's very easy. If not, you have to derive it using second Newton's law or Euler formula. It's very easy to derive.
Okay, no problem. No problem. I'll make it.
So good luck to you on your...
Thank you very much. By the way, I wrote to the teacher. I told him that you were a very good tutor.
Thank you very much. Thank you very much.
No problem.
If you have any questions, just send me an email. I'll try to find some time and to respond to you. No problem.
No problem. Thank you very much, and good luck to you too.
Thank you very much. Good luck. Thank you very much.
Have a good day.
Have a great day.